Okay, good morning. How are you guys doing? Excitement, right?
Pretty good. Did you have a good
Post
contest?
contest haze. Okay, let me make a few announcements before we start, learning new stuff. Your contests are graded. So some of them got graded sooner than others. So some of you had it for a little while, and some of you maybe it should just be visible now. Solutions for the contest are also up. So please take a look at your contest comments and look at the solutions. And if you have any questions, you can send them to me via email or meet me and collaborate if they're hard to explain in an email. I also graded the vector addition lab, and some of you got perfect scores on it, although that's very few. Others lost a few points, and some people lost so many points that you got a 0. Now, in all of those cases, I expect you to get 100% on the lab. So if I took lots of points off, but the intent is for you to go back and fix your mistakes and get 100%, and hopefully as you get in the swing of the labs, maybe you're getting closer and closer to getting everything right the first time around. So I might have been a little extra hard on the first lab to sort of set things in the right stage, I guess. So if you have mistakes on your lab, you should go in and make corrections to your original document. Please do your corrections in a different color so it's easy for me to see what's the new stuff. And then you just resubmit it. You go back to the lab assignment and you click it, and you have an option to submit it again. And so you'll submit it again, and it's going to show up for me as something that needs to be graded, and I will reassess it. And you absolutely can get 100% if you make all of the corrections. Okay, so you shouldn't be worried over much about it, but if you don't mind, I don't have a real firm timeline in mind, but maybe try to get corrections done within about a week or so, so that you don't kind of forget too much what you were doing, and I don't forget too much what you did wrong. And do not erase your bad stuff though. Don't erase the mistaken stuff, because then it's harder for me to see what you changed. So leave what you had, but just add to it whatever you need. So in some cases, it's probably pretty clear, but if it's not clear, just send me an email or meet me after class and collaborate or something, and I'll try to make sure it's clear. I will work in the next couple of days to get the next lab, the projectile motion lab, graded. I'm trying to juggle all these things, but my priority is always going to be grading exams. So when I have an exam to grade, I'm going to make sure I grade that first, even if a lab was turned in earlier, because for me it's more critical for you to get the feedback on the exams right away. Okay, does anyone have any questions about that? Okay, these exams were much better. I should have prepared like a spreadsheet with the data, but there were a good number of A's this time. That's good. Very low number of failing grades, which is also good. A lot of improvement, even people who didn't get such a great grade, as well as I think you can do. I still saw improvement for a lot of people. And some people are probably going to be kicking themselves because they really had it down pretty well, but made a few dumb mistakes, what I call dumb mistakes, silly mistakes, that probably brought the grade down from an A to a B. So I think definitely the people who are still in the class are doing the right stuff. If you feel like it's not going well, you feel like something's wrong, the study time you put in is not working, meet me and collaborate. People who have been meeting me and collaborate, I've seen a lot of, positive progress, and I see generally good performances from those people. So, if I were to comment about this last contest, you know, we had 2 problems that were on vectors, adding vectors, and then we had 4 problems that were on the projectile motion stuff. If you are having trouble with the projectile motion, that's not so critical, but if you're having trouble with vectors, that's going to cause you a lot of trouble going forward. So please make sure, if you're still struggling with vectors, that you talk to me and get some help to get yourself ready. If you're missing stuff because of not interpreting problems correctly from English into math and kind of messing them up a little bit, we're going to continue getting practice on that process, so you'll keep getting better at that. Okay, so I think that's it for my announcements. So let me get my whiteboard up and review a little bit what we were talking about last time. So, one thing I did want to mention, I sent an email to the section 230 to that class. So this is really for people who are listening to the recording later. People in section 230, the video from Thursday's lecture, somehow I thought it was posted for you to see, but it wasn't, and I didn't find that out until last night. So please go back and watch that. I sent an email, but please go back and watch that really before you watch this one. So if you're just starting to watch this lecture, you should stop it, go back and watch the 8, and then you'll be ready for this one. Okay, so let me quickly remind you what we were talking about. We were talking about Newton's laws, and the first law, my whiteboard is acting up already. The first law is called the law of inertia. And it basically says that objects in motion tend to stay in motion. Boy, that's not really legible. Let me change my pen tool a little bit. Objects in motion stay in motion, and objects at rest stay at rest. And the fine print is, if an object is in motion in a straight line at constant speed, it will stay in motion in a straight line at constant speed. And so if we see something, even if it's constant speed but it's not in a straight line, then that's not inertia. That there must be something to explain why it's not going in a straight line. So the planets are a good example of that. They keep moving forever. They don't move exactly constant speed, but if the orbits were perfect circulars, they would be constant. Perfect circular orbits, they would be constant speed, but they're changing direction all the time, and it's that change in direction that Newton had to explain. The second law, so the first, I wrote it mathematically, it would say A equals 0. Things don't accelerate on their own. The second law says, but sometimes they do accelerate. So why do they accelerate? They accelerate when there are forces. And so the sum of the forces, again, this symbol, this is, if I make it neatly, it's, it looks like that. Let me make it look like that over here. It's the Greek letter sigma. And it's a mathematical symbol that says sum, mathematical sum. Add up the forces. It's an instruction. If we add up all the forces and find the sum of those force vectors, then that net force divided by the mass of the object will determine the acceleration of the object. And this is primarily what we want, what we need to work with today. And there was the third law, that mathematically we could say the force of object 1 acting on object 2 equals minus the force of object 2 acting on object 1. So in words, this is sometimes said as, for every action, there's an equal and opposite reaction. What it really means is, I don't like action or reaction, I like interaction. When things interact, then there's a interaction between them. And that interaction, on one side of the interaction, an object 2, it looks like one thing, and object 1, it looks like something else, but because they're really coming from the same, the size of those interactions, the size of the forces must be the same, and the direction is always exactly opposite. Okay, so we'll get some experience with that, maybe at the end of today, but possibly not until tomorrow. But today we really want to focus on using the second law to find the acceleration for really any situation that we come across. So let me start a new page, and we'll just get a little example going here. So suppose we just have, the floor of a room, and then we take an object and we place that object on the floor, and then we start to exert some forces on the object. So maybe the force, let's make it kind of not too big of a force. So there's a force acting on the object, and I'm going to call that the applied force. And suppose that applied force has a magnitude of 20 newtons. And maybe the mass of the object, let's call this m, and we'll say the mass is equal to 10 kilograms. And suppose I want to find the acceleration of this mass. So that's where Newton's second law comes in. However, I'm not ready to use Newton's second law, because the instruction of Newton's second law, it says, net force equals ma. By the way, I'm not expecting you to remember which law is which, okay? But what I'm expecting is, if I give you a situation, you can find the acceleration. Okay, so the instruction is sum the forces, add up all the forces. So I only have drawn one force acting on the mass, and I need to draw in all of the forces, because Newton's second law doesn't work unless we include every single force acting on the mass. So can anyone tell me another force that would be acting on the mass? I have to get them all before I can solve for acceleration. Can anyone tell me another force that would be acting on the mass? Dustin?
Gravity.
Yeah, gravity. So gravity, we know gravity points downward. The force of gravity is kind of big in this particular problem. Okay, we'll learn how to find how big is, pretty soon. Okay, are there any other forces acting on the mass? Ziad?
Force of friction.
Okay, which way would that point?
The opposite direction.
Opposite to what?
To the force that you're applying to
Okay,
20 newtons.
so would it be 20 newtons?
Well, not exactly.
Oh, okay. Which is opposite to the 20 Newton force. Yes, I'm in agreement. So it will point backward, and we don't really know how big it would be necessarily right now. Okay, that's okay. Are there any other forces acting on the mass? Okay, let me ask you this. If I would add these three vectors, think about our vector addition lab. If I would add, so just imagine, here, let me make that black. If I were to add them, just tail to head, we would have, the F applied, and then if I add the force of gravity, it will point, downward, and then we add in the friction force. The resultant force will point this way. So this would be the net force. The resultant vector is the net force. And if that's what's going on in this problem, then it looks like this object will move pretty much down and slightly to the right, at least based on the size of the vectors that I drew. Is this object going to move down and slightly to the right? I can't see you shaking your heads no, because, you know, I'm looking at my whiteboard, and anyway, most of you have your cameras off. Should turn them on. But the answer is no. This object is not going to move down or down and slightly to the right. So we must not have all the forces. Okay, we must be missing something. Does anyone have an idea what other force we might be missing? So we might not know an answer to that question because we don't have the language for it. So maybe we don't know the name of whatever it is, but what is the reason why the box is not moving down? Okay, force of the earth, Elena says. Yeah, I mean, the ground must be exerting a force on the mass. I don't want to say the earth because I think of the force of gravity as the force of the earth, you know, but I know what you mean. The ground is pushing up on the box somehow. Now, the question is, which way does it point? You know, does it point just up like that, or does it point, you know, up there somehow, or maybe it points back like that? I'll tell you what, I'm going to give you three choices. And I'm really only talking about the direction of this thing, not how long I'm drawing it. But let's call it A, B, and C. And I want to know what you think if one of these is correct, and if not, you can pick option D. Okay, so D would be none of the above. What do you think is the direction of, and we're talking about the force between the floor and the box or whatever it is? Okay, so the responses were, let's see, we had 2 here, 10 here, 0 here, and, you know, 2 for option D, none of the above. Okay, so most people are saying it points straight up. A few people are saying it points kind of backward a little bit. And a few people say, I don't think any of those. If you don't think any of them are right, do you have a different idea that you could share?
I don't have a different idea. I just don't think that those are right. I'm not sure though.
Okay. All right. Well, then let's kind of consider them. How about option A? A couple people picked that. Why do you say option A? Someone who picked option A. Haley?
I said option A just because like when we were drawing, like we were adding the vectors and we were
Can
saying
you
that
speak
like
up a little bit?
oh sorry. I picked it because can you hear me now? Is that
Yeah,
good?
not me.
When we drew out like the vectors, we were having like the sum of the vectors pointed down this way. I just thought option A would be pointing kind of like opposite of that to kind of like counteract it, but that was just my thinking.
Okay. All right. That's a good, yeah. So I kind of erased that from the screen, but you're thinking you need a fourth vector to sort of bring us back to 0. Yeah. Okay. That's an interesting thought. Okay. So let's take Haley's thought for a second. If the fourth vector would, so let me kind of draw what I had again. It's pretty bad, but okay. So if we have something here, okay, so it goes down there, and then down here, and then back here. And then we said that, you know, the resultant vector would be pointing down to here. So what Haley's really suggesting is that maybe we need a fourth force that does this, and then when we add them up, we get 0. And that would be the case if this thing is not going to move. This thing's not going to move at all. It better be that when we add up all the forces, we get 0. On the other hand, if it is going to move, which way is it going to move if it moves? Anybody? It's going to move only to the right, right? So really for that fourth vector, let me pick a different color. The fourth vector could do this. It could do, you know, it could do anything along these various lines. I'm getting a lot of lag on my screen, so just give it a second. So it could do any of those things. And then our resultant vector would either be a little one to the right, or it could be a big one to the right, or it could be kind of a medium-sized one to the left. And it would still then accelerate to the right or to the left. Now, probably accelerating to the left would be weird. So it can't point too much to the left. All right, what I'm trying to illustrate here is that it's really tricky for us to know about what forces there are and which way they're pointing and what they look like, because we cannot actually see the forces. Okay, we can't see them. So there's a really kind of a nice trick to help you know, A, if you got all the forces, and then B, which way the forces might be pointing. Okay, so I kind of introduced this problem so that we are open to a trick. Okay, so let me erase A, B, and C here. And now, with our forces, when we're trying to add in forces, here's the rule. Okay, except for gravity, I'm going to talk about gravity separately, but every other force that we will talk about requires contact. Okay, it requires there to be contact. Now, gravity is different. It's like magic. Just, I mean, for a second, let me turn off the whiteboard so you can see me. But just look at my pen. When I let go, it just goes down without anything touching it. And that doesn't seem like magic to you because you see it all the time, but just imagine I let go of this and it shoots to my left. If that happens, you're going to go, wait a minute, you know, that you think there's someone with a string, like some fishing line or something, that's making it swing sideways instead of falling down, because there's no way I can let go of this and it's going to move any way other than down, because we don't, if that happens, that's magic. Okay, and gravity is like magic, but it's just magic we're used to. So all of the forces except for gravity, they require contact. So if you want to know how many forces there are in a particular situation, all you have to do is find where the contact is happening, and then that there should be a force there. So in this problem, there's a box. Let's kind of go back to the beginning. There's a box, it's sitting on the ground, and then I pull it with a force, an applied force. So my applied force must come from contact. I'm either pushing it from behind or I'm pulling it from the front. Ziad, question?
Professor, we can't see your screen or the black.
Thank you.
No problem.
That's the danger when I take my screen away. Anyway, you were just missed me erasing a bunch of stuff. So back to the beginning, the contact acting on this box, first of all, there's me applying a force. Like I was saying a minute ago, I'm either pushing it from behind or I'm pulling it from the front. It doesn't really matter where I'm touching it. Either way, the force is a force to the right. And so I always draw it like it's pulling away from the object, but it doesn't really matter whether I'm pushing or pulling. The important thing is there's a force to the right. And the only other contact on the box is from the ground. Okay, the only other contact is from the ground. And so there must be 3 forces total. There's 2 points of contact, me touch box, and the ground, the floor. And then gravity is like magic. It's an extra force. So when we want to know how many forces there are, we count the points of contact, and then we add 1 for gravity if there's gravity in the problem. Okay, so we have the applied force, we have the force of gravity. There can be only 1 more force acting on this box. Okay, there can be only 1 more force. Now, if I have a force that moves to the right and a force that's pulling down, and then if it's going to move to the right, my third force, it's got to point upward somehow, like I indicated before. It can point up and to the right, it can point straight up, it can point up and to the left a little bit. What it's probably going to do is it's going to go something like this. This is assuming we're pushing with enough force for the box to move so that the resultant force, the net force, will point to the right. Okay, so going back to my picture, this force of contact between the ground and the box is probably pointing up and to the left somewhat. Okay, and those are the 3 forces acting on the box. That's it. Now that's the reality of what really happens. Okay, now I don't know if the box is going to move or not because I don't know how far the contact force is leaning backward. Okay, when I'm not pushing on the box at all, then the contact force will just point straight up. As I start to push on the box a little bit, then the contact force, so let me kind of use, we'll do this. So when I'm not pushing on the box, oops, that's not a very good line, is it? When I'm not pushing on the box, then the contact force is going to look like that. Now, as I start to push on the box, what's going to happen is the contact force is going to start leaning back. And it's going to lean back and lean back and lean back, always in such a way that its vertical component must be equal in size to the force of gravity. And that is to keep it from going up or down. And its horizontal component, as it starts to kind of push backward, this horizontal component is what we call the friction. Okay, so Ziad had wanted to add a force that's called friction, but what really is happening is there's this contact force. Okay, there's a contact force, and we just sort of artificially, just as humans, when we're trying to do math, we decide to take this vector and split it into x and y components. And the x component of that vector is the thing that we call the friction. And the y component, we have a different name for that. I'll tell it to you and I'll explain why it's this, but it's called the normal force. Okay, so normal force. And normal is just a mathematical term that means perpendicular. Okay, so it doesn't have to do with like normal versus abnormal or it being an ordinary force or regular or something like that. Normal is a math term that just means perpendicular. So what's exactly happening here? We have a contact force. That's the force that comes from the box sitting on the surface. Now, that force comes because the surface is solid, and it does not want the box to sink into the surface. If the surface were mud or something, then the normal force wouldn't necessarily be as big as the force of gravity, and this thing might start sinking down into the mud. But if it's just a normal floor of a room or the ground, something solid, then the normal force will typically be the same size as the force of gravity to ensure that the object doesn't fall through the matter. And then that's the perpendicular component, meaning it's perpendicular to the ground, perpendicular to the surface. Normally that would be in the y direction because our surface is normally in the x direction. Then the horizontal component, the piece of the force of contact that is parallel to the surface, is called the friction. Now, if you had physics before, you probably just learned about these two forces and they were just called different forces. And that's perfectly fine when you're solving problems, but conceptually, I like to make sure we're aware that they're really just pieces of one contact force, because that will allow us to properly count how many forces are in the problem. So in this picture, there are 2 points of contact, so there should be 3 forces. And I don't want to think of normal force and friction force as separate forces, because then I have 4 forces. Okay, there's 3 forces. There's 2 forces coming from contact, and then the force of gravity, which is like magic, and which would be there even if I lift the box up in the air and drop it. The applied force would go away, and the force of contact would go away, but the force of gravity would still be there. Okay, so in this problem, the question is, we want to know the acceleration, and we do not know how far back the contact force will lean. If you did the lab already, you saw that as you start to push on an object, the friction force gets bigger, which basically is equivalent to this contact force starting to lean back. But it can only lean back so far. And at a certain point, it can't lean back any further. So maybe it only leans back so that the friction force can, at the largest, be 15 newtons. And once it leans back so that this is 15 newtons, it kind of breaks free of the friction and it starts to slide. But we don't know that. So to make this problem a little easier, and for the first several problems so that we can learn how to use Newton's second law, because friction really adds a complication, we're going to say that this is frictionless. Okay? So if we say that it is frictionless, then we can erase all the friction and the contact force, and what we would say is that we really just have a normal force. Keeping in mind that that is, in this case, would be the entire contact force. Okay, let me pause and see if there are questions, because this is, even in a live lecture in class, this is often a kind of a weird and difficult concept. I just want to make sure everyone is getting the idea here. Any questions about this normal force or friction or contact force? Ziad.
So we're gonna say it's frictionless because we don't know the force of contact and the friction.
we're going to say it's frictionless in this problem because we don't know how to deal with friction yet. So I'm going to just sort of say, suppose this is on ice or something, so that we don't have to worry about friction right now. Mainly, I want to make this a simpler problem so we can learn how to do it. And then once we know the process, we will go back and do examples like this, but including friction.
Thank you.
Sure. Okay, Haley.
Okay, so are we just assuming that the normal force, I know we said is perpendicular, so it always is pointing like straight up and down, even as the like component, whatever the FC starts like leaning back?
Yeah, that's right. I wouldn't say it's always up and down because this could be like on a hillside or something. And if it's on a hillside, then the normal force would actually be pointing still perpendicular to the hillside. But yeah, exactly. As the contact force starts to lean back, if there's friction involved, as that contact force starts to lean back, the normal force still represents the part of the force that is vertical or perpendicular to the surface. So we will see it in more examples and see how it works. But yeah, that's exactly right. So if I have drawn these three forces, and I know that that's all of the forces. And again, I do know it's all the forces because this problem has only 2 points of contact. I should have only 3 forces. Now, technically, friction could be added in normal force as part of that force, but this problem now says it's frictionless. So then I'm ready to write down Newton's second law. So we say net force equals ma. And remember, Newton's second law says add up the forces. And what we know from the last contest and from our vectors lab is if we want to add up vectors, what do we have to do to those vectors? What do we have to know about the vectors in order to be able to add them? Ziad?
You need to know their x and y components.
Exactly. And so what happens is we take Newton's second law and we actually split it into a Newton's second law for x components, which says add up all of the x components, and you get mass times the x component of the acceleration. And then a second Newton's second law for the y components that says add up all of the y components, and this should be equal to m times the y component of the acceleration. Okay, this is what we do every single time we want to use Newton's second law. We have to split it into one equation for x components and one equation for y components. And if we were doing some really weird, hard problem with like electrons moving in spirals through magnetic fields, then we would have x, y, and z components. We would have three-dimensional space, which we won't do that in this class, but conceptually it's there. So now, once I split it into the x and y components, my strategy is to ask myself which component seems more important, okay? For example, in this particular case, we know that the object is going to move in the x direction if it moves at all. Because there's no friction, it will move, okay? As you saw in the force lab, if you don't have friction, as soon as you start applying a force, the object starts to move. But it will not move in the y direction. So I know, for example, that ay will be 0. How do I know that exactly? Because I know from this picture that it's going to move only in the x direction. So my acceleration vector should be pointing to the right. Remember, acceleration has a direction. This will accelerate to the right, and a vector that points to the right does not have a y component. Okay, it only has an x component. So all of that tells me the x direction is the most important one. So then I come in and I fill it in. I add up all of x components. I would have the x component of the normal force plus the x component of the force of gravity plus the x component of my applied force, and that's going to be equal to m times the x component of acceleration. But this one is pretty full because the normal force doesn't have an x component. Remember, something that points upward, each vector, if you recall, each vector kind of lives on its own axis. And so this normal force points at 90 degrees on its own axis, which is the y-axis. It does not have any x components. And so I can just, without really doing anything, in fact, in the future, I wouldn't even write down nx because I would just realize it doesn't have an x component. And the same goes for the force of gravity. It also doesn't have an x component. And so how about the applied force? Well, the applied force's x component is the whole thing. So that is, Fx is just equal to the applied force in this case because the applied force doesn't have any kind of angle. So we have F applied times m times a sub x. And we want to solve for a sub x, so from the algebra standpoint, it's pretty easy. We just divide by the m. And finally, AX would just be 20 newtons over 10 kilograms. And, the units look a little weird. What units do we expect? We expect to have meters, so this should be 2. And we expect meters per second squared. How does that work exactly? Well, a newton, if you recall, is a unit of mass times a unit of acceleration. And then when we divide by kilograms, the units of mass just cancel out. And so we get meters per second squared. However, I recommend that you never, ever write this out and do it that way. You just instead should learn to trust that if you're working in the metric system and your forces are all in newtons and your masses are all in kilograms, then your accelerations are going to be meters per second squared as they should be. Okay, any questions about this problem? Notice I never needed the y components in this particular case. I didn't need it. If I had worked with the y components, if I had worked with them, let me just erase this thing with the units here. Okay, so if I had needed to work with the y components, I would have said, the normal y component plus the force of gravity y component equals 0. The normal y component is just the whole normal force. And the force of gravity y component is negative whatever the size of the force of gravity is, which we don't even know how to find that. Okay, so maybe I can write it as a magnitude to make it clear that what's happening. The force of gravity, I just write the symbol Fg, that means the size of that force, but its direction of its y component, the sign of its y component is negative, so it would get a minus sign there. Now ordinarily I wouldn't write the absolute values in because it just gets kind of clunky. And at the end of the day, what we find out is the normal force is just equal to the force of gravity. And again, we don't know how big the force of gravity is, but however big it is, suppose it's 50 newtons, then the normal force must also be 50 newtons to keep the box from moving in the vertical direction. And that's what the normal force is there for. It's there to make sure that the acceleration in the perpendicular direction is 0. In this case, it's equal to the force of gravity, but that will not always be the case. It's just the case in this problem. Okay, Any questions? All right, well, if we want to go any further, we really need to know how to find the force of gravity. And so let's just try to answer that question. So how big is Fg? Well, all we have to do is take the box and drop it. If I drop the box, then the only force acting on it is the force of gravity. So when I do the sum of the forces equals ma, and I'm splitting this into the x direction components and the y direction components, I don't care about x direction because there are no forces with x components. I only care about the y direction. So that would say sum of the y components of forces equals m times y component of acceleration. We know the acceleration points downward, and we even know that it's equal to negative g. That is a y, the y component would be negative g. So this would be m times minus g. We know from our whole last chapter that ay is equal to minus g if something is in free fall. And the sum of the y components of forces, well, we're just going to have the force of gravity y component, which gets a minus sign because it's down, and the magnitude of that component is just whatever Fg is. So looking at this equation, it's really clear that the minus signs will cancel and tell us the size of the force of gravity. So in this particular case, that's 10 times 9.8. And again, without even writing the units, I know that this is a force, and so its units should be newtons, as long as I kept my mass in kilograms and my acceleration in meters per second squared. Okay, so in general, let's just put, a bright green box around this. Anytime we want to find the size of the force of gravity, all we need to do is take the mass and multiply it by g. And that will give us the force in newtons. Now, we're already, just as humans, we're used to measuring masses of things and thinking of that like it's weight. If you are a nurse and a patient comes into your place of work and you weigh them, you get their mass in kilograms, and we just treat that like it's the weight, even though it's technically the mass. If we want to make it a weight, which would be the force of gravity, we have to take that mass in kilograms and multiply it by 9.8 to get the force in newtons. But you can kind of think of the g as a conversion factor to convert from kilograms into newtons. If I have a 100 kilogram box, that becomes a 980 Newton box. Okay, so any questions about finding the force of gravity? Okay, so let's try to modify the previous problem, make it a little bit harder. And there's my box. Let's suppose that we apply our force, same applied force. So I'm going to make it about the same length, but pointing up at an angle. Maybe 30 degrees. So there's my F applied. And it's still equal to 20 newtons, but now it points up at an angle. And I want to find the acceleration. Again, we're going to say it's frictionless. So how do I solve? Well, step one is to draw in all of the forces, okay? After we've done a couple problems, I'm going to write down a series of steps. So after we see everything that can happen, I'm going to write down steps, and that's going to be your pattern that you follow when you're solving any problem with forces. So step number one is draw in all of the forces. We have to make sure we get them all. So someone tell me another force that would be acting on this thing. Gravity. Okay, good. So we saw, now how big is gravity? We saw that it's 98 newtons. If this is the same box, 10 kilogram box, then 98 newtons is a lot bigger than 20. So that force of gravity is, I'm going to draw it, it's about as long as I can get it and have things still working out okay. Okay, so there's my force of gravity. And what other forces might be acting on this box? Okay, let me say this. How many forces should there be total on the box? Three. Haley says three. That's right. So there's 2 points of contact, the ground and me pulling the box. And then there's gravity, which is like that sort of magical extra force. So I have 2 forces already. I must have another force. What's the other force? Ziad?
The normal force
The normal force. Which way does that point?
pointing upward.
Just pointing upward. How big is the normal force?
Isn't it just the opposite of gravity?
That's a good question. Let me do a poll. So is the normal force just the same size as gravity but opposite? Let me see what you think. All right, looking for maybe 1 or 2 more responses. Okay, so I'm seeing 7 to 7 with 2 people who are in the bathroom. Or maybe, no, they're not in the bathroom. They're having a snack. 2 people having a snack in the other room. Okay, so let's figure it out. We don't have to guess. We can figure it out. So how do we do this? There's my normal force. I am going to write down my Newton's second law. Net force equals ma, and split this into the x and y components. In the x direction, we're going to have only one force with an x component. So when I'm summing the forces, x components, like in the last problem, the normal force and force of gravity don't have them. So only the F applied has an x component. This will be m times ax. And in this direction, we're going to have the normal force, which is its own y component, and then the y component of the applied force, and minus the force of gravity. So the force of gravity is its own y component because it points only vertically, and it gets a minus sign because it is down. And the question is, is AY still 0? Because if it's still 0, we can find the normal force, but if it's not still 0, that's going to be tricky. Think about that for a second. What do you think? is this thing going to accelerate in the y direction? Meaning, is it going to go up because I'm lifting a little bit, or is it still just going to move sideways? Let's do a poll on that. Okay, let's do a poll on that. Is AY equal to 0? Acceleration in the y direction equal to 0? There's the poll. Who says it is equal to 0? That is, if you think it's equal to 0, this thing will not go in the air. And if you think it is not equal to 0, you think it's going in the air. Okay, so we have 11 to 3. So I agree with the majority in this case. AY is 0. How do I know that? Because in order for this box to go in the air, I have to be lifting with a force bigger than the force of gravity. If you look at the size of the force of gravity, remember it's 98 newtons from the last slide, and I'm only lifting with, I'm pushing a force of 20 newtons, and only a piece of that 20 newtons is upward. So I'm not lifting hard enough to bring this thing in the air. And AY will be 0. Now, I know that may not be totally clear yet because we're still new to this and getting experience, but it's not. And when we finish this, we'll see, or that is AY is 0. It's not accelerating in the air, and we'll see why as we complete this. So the normal force would be equal to the force of gravity minus FAY. And we know the force of gravity already. But how do we find the y component of a vector? Anyone remember how to find the y component of a vector? I know you remember. How do you find the y component of a vector? Siad.
You take the magnitude multiplied by the sine of theta of the angle.
That's right. So in this case, the magnitude is FA. So we can say FA sine theta. That's going to be 98 newtons minus 20 sine of 30. 20 sine of 30 is 10 newtons. So it turns out the normal force is 88 newtons. This time 98. So it is not as big as the force of gravity. Okay, it's not as big. Why is that true? Basically because the normal force is lazy. Okay, it's a lazy force. It does not do any more than it has to do to make sure that the box doesn't slide through the matter. It's never going to overdo it so this box just jumps into the air. Normal force is not that way. It's extremely lazy. It's like, not you guys, but like some students who are not going to do extra work if there's no points. I know you guys are different, but you know, there's no benefit to the normal force being any bigger than 88 newtons. If it gets any bigger than 88 newtons, this box has to jump into the air. Okay, normal force does not want to do that. So because the y component of FA was 10 newtons, as soon as I start lifting, and I've got 10 newtons worth of lift, the normal force just goes down to 88 newtons. Okay, so it is not the case that the normal force is equal to force of gravity. I want to stress that so much. It is only equal to the force of gravity in very rare circumstances. In physics problems, it's not so rare. It winds up being about 50% of the time. But the other 50% of the time, it's not true. And it's only true that 50% of the problem is because we make artificially easy problems. Okay? There's no fundamental deep connection between the normal force and force of gravity. It's just the case that on the last example, we had two forces in the y direction. We only had two things y components, and so they had to add up to 0, and that means they're negatives of one another. But as soon as I have three forces in the y direction, there's no reason why the normal force will be the same size as the force of gravity. Okay, so that was just kind of an aside to realize that the normal force is not going to always be as big as the force of gravity. But in our problem, what we want is the acceleration. That means we have to come to the x direction. We will need to know how to find normal force, so this is not useless. The way we find normal force is summing the components in the normal direction and seeing how big normal force has to be. But in this particular problem, we don't need that. So we move on and find our acceleration, x component. Justin.
Where in the equation did you get divide by the 10 newtons? Is that just you just divide by the mass of the object?
Can you speak up a little bit? I can barely hear you.
Where did you get dividing by the 10 newtons?
In the last problem?
Yes.
Or you mean
In the equation that you just...
Oh, this right here? This
Correct.
20 sine of 30 divided by 10 newtons?
Yes.
Yeah, sorry, that's not a divided by. That was supposed to be kind of like a squiggle to say that this number is equal to 10 newtons.
Gotcha. Thank you.
Okay, yeah, sorry, that was a little unclear. Okay, so going back to the x direction, our x component, just like to find the y component, we use the magnitude times sine. To find the x component, we use the magnitude times the cosine. And that's equal to m times ax. And so ax is just f applied cosine of theta over m. And that's going to be 20 cosine of 30 over 10. So that's about 1.732 meters per second squared. And so what happens is, by lifting a little bit on this box, some of the force I'm using is, in a sense, wasted. All it's doing is taking the load off of the normal force. And the rest of the applied force, what's left, results in a smaller acceleration. We had 2 meters per second squared last time. It's reduced to 1.7 roughly meters per second squared because my entire force is not pointing in the x direction now, only a fraction of it. It turns out it's only 17 newtons left in the x direction. And so we get a smaller x acceleration. All right, any questions? All right, let's take a 5-minute break, and when we come back, we'll try to get into some more complicated problems.